Hello friends, in the last class we were discussing the integral and derivative control modes, okay, and in the previous class to that we were discussing the proportional control. So individually we have proportional control, integral control and the derivative control, okay, and now let's look at the composite control modes, which are PI, PD and PID, okay. So they are the most popular controllers in industry, okay. So let's try to understand what makes them popular, okay. So as we have seen, the proportional controller, we have the integral controller, we have the derivative controller. What are the advantages of each one of these controllers, and what advantage do we get when we consolidate these controllers as PI, PD and PID, alright. So what is the advantage of proportional controller? The advantage is that it is instantaneous. It reacts instantaneous, okay. It reacts instantaneously with respect to the error. Of course, the offset error will never become zero using a proportional controller. We have discussed this already, okay. When you take an integral controller, this reduces the offset error to zero, okay. And depending on the constant Ki, which is the integral constant, the rate at which the integrator would respond to a certain error curve will be different, okay. If you make this gain to be larger, then the integral control will be very aggressive, and if it is smaller, then it will be less aggressive, okay. So in any case, you are going to get the offset error to be zero due to an integrator. And what about the derivative controller? The derivative controller, the advantage, the primary advantage we get it is anticipatory, okay. That means we are calculating d by dt, okay, the rate of change of error. And if the error curve is not noisy, then the derivative control helps to correct the control output with a foresight of kd into d by dt. So this will be equivalent to the control output p. Okay. So now let's look at the advantages of combining these controllers. Okay. Combining these controllers. So if I combine P and I, what could be the advantage? So let's say if I combine PI control, what could be the advantage? I would be able to see that the controller responds instantaneously with the error and the offset error is zero. A very good combination, okay. And if I have a PD control, then you would see that the controller output is instantaneous, and also it can anticipate the changes in the error. So this is also a good solution when there is no noise, okay. However, in this combination of PD, you will lose the advantage of offset because you don't have the integral mode in it. So in the PD mode, you will see that you will have an offset error always, okay. So still there are some control systems where the PD control is used, where the offset error does not make much difference to the control, alright. So in PID, what is the advantage of PID now? PID combines the advantage of all modes P, I and D, and therefore the most popular solution, okay, the most popular controller since decades, okay. And then if you look at the P control mode, you have a gain of Kp. In I control mode, you have the gain Ki, and in D control, you have the gain Kd, okay. And these are the gains which needs to be tuned for a given process, and when we tune this for a given process, we call it as tuning, or I can call it as PID tuning. There are certain methods which are used to guess what could be the value of Kp, Ki and Kd when you start a certain control system, or when you actually design the control system, okay. And of course, it is this tuning is based on the open loop and closed loop responses. Of course, we'll see this little later, okay. So let's quickly see what is PI control. As I told you that it combines the proportional mode and the integral mode. Of course, this PI of 0 is from the last value of the integration, okay. The previous value of the integration where the error went to 0 is PI of 0, okay. So it combines the advantages of both the proportional control and the integral control. Now, if you look at this graph, this is a reverse action controller. As I told you that reverse action controller means that if the error increases, the control output should decrease, okay. Direct action means if error increases, the control output will also increase. There could be situations in both ways. Okay. So in this case, the plot here is shown. The first subplot is that of the error, second subplot is that of the controller, and the controller is reverse acting controller, and this is a PI controller. Okay, there are two components of it. One is the proportional component, you can see clearly, which is something like this, right? So this is the proportional component of it, which is almost resembling the upper error curve because it's proportional, right? But since the controller is reverse acting, you can see a reverse triangle here. Okay. And the integration is integral control action. The second part is shown something like this, right? So this part is the integral component. Okay, you can see that this is an reverse acting integral controller. This is just integration of this curve, right? Even if you do piecewise, it is going to look like this. For a straight line, you will get a parabola kind of thing. Okay, that's the thing. So if you combine these two control actions, you are going to get a composite control action, which looks something like this. Alright. So this is the way you represent or you combine the proportional integral control action to show the composite control action. Okay. So that means you just have two components here. One is the proportional action and then the integral action, and this comes from the last value of integral action output, which is represented by P of 0. Alright. So in this kind of action, you don't need to put P of 0, which is called the nominal value of the control output, because anyways the integration will take care of that. Okay, we need not really use any fixed value of P0 here. Okay, whenever we use an integral controller, or in any of the composite control modes, we never use P0. We just take care of this value, which is Pi of 0, which naturally comes from the integration. Okay, now let's go back to the next set of controller, the composite control mode, which is called the PD control, wherein you combine the P control action with the derivative control action. Okay, so you have to note here very carefully is that the proportional gain is getting multiplied by KD. Of course, in the previous case also, you see that the proportional gain is multiplied by the gain KI of the integration. Okay, you are multiplying the KP also with respect to KI. So there is a strong reason behind that, which makes it a little easier to analyze the contribution of the integral controller with respect to proportional controller. You want to show the contribution of the integral controller with respect to proportional controller. You would just try to multiply this KP into KI. Okay, so when you actually plot the curves, you will be able to see the contributions individually. Okay, so that's the reason why they have given this multiplication factor here, Kp into Kd. Okay. So as I told you that in a PD controller, the main advantage is that the proportional controller is instantaneous and this is anticipatory. However, you will not have any kind of offset reduction because you don't have an integral component here. And these two components are mostly instantaneous. One depends on the anticipation of the error over time, and the other one is multiplying the error with some gain constant Kp. Okay. And therefore here you require some kind of P0, which is the controller output at a nominal P value. Okay, so this is like controller output. All right, controller output at zero error condition. I can say, okay, at zero error. Okay. And of course, this we need to, since we don't have an integration component here, we need to change the value of P0 for every steady state change in load. Okay, and therefore we need to do some kind of manual reset here. Okay, manual reset. Okay, so all the disadvantages of the proportional controllers will keep haunting when you actually use a the composite control mode called the PD controller. Okay. So this is the way to understand PI and PD control modes. Okay. So if you see the PD control mode, this is also a reverse acting control. Let me write it properly here. So this is like reverse acting controller, wherein you see that as the error is increasing, the control output is decreasing. You can see very clearly that the proportional response is exactly what we have here, okay, and the derivative response adds to the transitions, and together they are going to give you a certain kind of response which is shown like this. So you have the proportional response which is almost like a triangle here, and this one, right, this is the proportional response. I think we should be seeing here, okay, this is the proportional response, and wherever you see the sudden steps, right, this step and this step, this is due to the derivative response, okay. So added up, you are going to get a composite response which would be helpful in dealing with change in error like this, alright. So this is the way to understand a PD controller. And of course, once you solve a problem, you will be able to understand how this control action works, okay, how does this control action work, okay. So let's try to see the numerical example little later after we discuss the PID control, okay. So as I told you, now PID combines all the advantages of the individual control modes, the proportional, integral and derivative control modes. Only thing to note here is that you are multiplying this gain Kp to all the terms, okay, to all the terms, okay. So in that way, the advantage you get is you can actually quantify how this integral control mode or derivative control mode, depending on a certain type of error, like a constant error or a ramp changing error and so on, can be replicated by this integral mode or the derivative mode, okay. That's the only reason they have done this multiplication of Kp to Ki and Kp to Kd, okay. And since you have the integral control, you need not really have this P0 term, which is the output of the controller at zero error condition, okay. Zero error condition is maintained by the integral controller by automatic reset, represented by Pi of 0, okay. So PID is the most popular controller where the controller works instantaneously. It has anticipatory capability of the error, and then also reduces the offset. Okay, 3 advantages in one controller combination called PID. Okay, that is the primary advantage of PID controller, and therefore it has been used. It is being used since long time. Okay. So if you see this very simple error curve, you have decreasing error. Based on that, you have this derivative term. Okay. So the proportional term will exactly look like the actual error curve. And integration would be integration of this one. So you have curvature, something like this. So it's like for a ramp, it could be like a parabola. Okay, something like that. Okay. Then when you add all of these three, then you get the composite control mode like this. Okay. So these curves are little not really so simple. So you need to add it piecewise. So here you see that error is decreasing continuously. It is quite easy to plot this curve even if you calculate mathematically. But then for composite curves, which is a combination of several types of piecewise curves, it becomes a little tricky to calculate the control output, especially for PID, PI and PD. Okay, let's try to understand one of these examples for PI and PD, and for PID it will be very similar to that. Okay, let's try to see a couple of examples. Okay, first let's talk about for PI controller an example which will clarify how does this how to plot the error, the control output for a given error curve. Okay, the control output for a given error curve. Okay, so if you see here, you have this error curve here, the piecewise different error curve, which is you see here that I have the error curve which starts from 0. I'll call this as P, this to be Q, and this is R. Okay, so this is a point 2, 2. Q is around 4 minus 3. Okay, just make an approximation here. And R is 6, 0. Alright, so this is the way just first you mark it. Okay, so you need to see between different time zones, the equation of the error curve should remain the same. Okay, then only we can calculate the composite control mode output. Okay, so let's try to first. So now I have 3 segments here. I would call it as OP segment. I would call this segment OP. Okay, segment OP, So in this segment OP, I have a relation EP is equal to T. So it is very straightforward. You can calculate the slope and find out. Okay. If you have the segment PQ, this bigger segment, and here you see that error would be represented as minus 2.5 T plus 7. Okay. So if you can calculate and see, it will be the same. So then you have the segment QR, wherein the error is represented as 1.5 times T minus 9. Okay. So this is a segment QR. Okay. So there are three segments. First segment, maybe I'll designate it differently. First segment, the second segment, and the third segment, and they have their own error curves. Okay. Now, what is the controller output? First, I will represent for first segment OP. I would represent the control output as P1, which is Kp into EP plus Kp Ki integral 0 to T EP dt. Okay, that's EP into dt plus Pi of 0. Okay. So here, if you get back to the example here, Kp is given to be 2, Ki is 2.2, and Pi of 0 is 40%. So for the first segment, I can take this directly as 40%. So that means this is the last value of the control output. Okay. When you start this error curve from here. So at this point in time, you have Pi of 0. If you draw the control output curve, Pi of 0 is 40%. Okay. Now let's try to evaluate this one. So what do we get now? So if you evaluate this one, you are going to get P1 is equal to 2T plus 2 into 2.2 integral 0 to T, okay, T into dt plus 40. Alright. So if I combine these terms, so if you find out this, you will get 2T plus 4.4, you have T square by 2, 0 to T plus 40. Okay, so this is the earlier integral component, right? Pi of 0. Now this is the new integral contribution. Okay, so the overall integral contribution for the next segment would be this Pi of 0 plus this one. So both of these would combine, and then this will be a new contribution coming up here. Okay, so that's the way we need to calculate. Okay. However, when we actually plot these curves for the control output, we need the time as a variable t here. Okay. Otherwise, actually here you have in the first segment the time ends at starts from 0 and ends at 2. Okay. So let's try to find at time t is equal to 2 what happens. Okay. At time t is equal to 2, the control output is 2 into 2 plus 2.2 into 4 plus this is the 40. Okay. So this is the total contribution of the integration at the end of the step. So this is, but the control output P1 would be 52.8, and then the integral contribution all alone from the previous step and this step would be 48.8%. Alright. So this is the way to evaluate the contribution of integral control for the next step. Okay. So now let's take the segment PQ. Okay, segment PQ, the second segment. Here T is between 2 and 6, and EP is equal to minus 2.5 T plus 7. And Pi1 of 0, I would call it as the previous integration component, yes, 48.8. Okay. Now when you evaluate this whole thing, so you are going to get P2. So I'll write it as I'll write the steps directly here. 5t plus 14 plus minus 5.5 t square plus 30.8 t. Okay, this is 30.8 t minus 39.6 plus 48.8. Okay, so this is actually Pi1 of 0. Alright, this is from the previous integration value. So at t is equal to 4, what do we have? P2 is equal to minus 5 into 4 plus 14, alright, plus of minus 4.4 plus 48.8. So this, the new integral component, which is called Pi2 of 0, will now be little different, which is 44 0.4. Okay, and the control output at P2 would be coming to 38.4. Alright, so you see that we have separated out the integral component term and we have added it to the previous integral contribution. So it comes to 44.4. Okay. Now coming to the third segment, which is segment QR. In the third segment QR, I am changing my time from 4 to 6. Right? Let me just check previously. So you have 4 to 6. Okay. The second segment is from 2 to 4. Okay. Second segment is from 2 to 4. So let me just correct this here, 2 to 4. Okay. So the third segment, I am changing T from 4 to 6. 4 to 6 here. Okay. Now, what is the error curve here? EP is equal to 1.5T minus 9. 1.5T minus 9. Okay. So what will be P3? The control output, you apply the controller equation, you have 2 into 1.5T minus 9 plus 2 into 2.2 integral 4 to T. So this is little, so you should always be careful that the upper limit you keep at time T so that it is easy for you to sketch the curve. Okay. Minus 8 Tt plus PI2 of 0. Okay. So this is 44.4 from the previous step. Okay. So let me write P3 completely now. So P3 would become something like 3T minus 18, alright, plus 3.3T square minus 39.6T plus 105.6 plus 44.4. Okay. So at T is equal to 6 seconds. So P3 would end up at 31.2%. Okay. And of course, we can calculate the next PI3 of 0 by evaluating this total 44.4 plus this additional term. Okay, what is that additional term? 3.3T square minus 39.6T plus 105.6 evaluated at T is equal to 6. Okay, so this is going to give you the complete value. Okay, so what you need to do is you need to sketch each of these control actions or each of these segments individually, and you already know what is the value of the control between the segments and what is the value of the control at these points. Okay, at these points you already know, and between this you have the equation of the control. Okay, so there are 3 segments and there are 3 equations, and therefore you can actually plot the control output. So what we have done specifically in this case is that from one segment to the other, we have taken forward the integral action part. Okay. So initially the integral action was around 40%, and then we added it to 48.8, and finally it has come to 44.4. And in the last segment, there is some value which you need to evaluate here. I have not done here, but you can always evaluate at T is equal to 6. If you evaluate this term and add it to 44.4, that would be the final value of integral contribution. Alright. So this is the way to solve a problem on PA control. Okay. So next we try to solve a problem on PD control. You have the same error curve. You are saying P naught as 40%. P naught as 40%. Okay. KP is 2 and KD is 2. So what is the control actions here? PD control output is P, which is given by Kp into EP plus Kp Kd dEp by dt. Okay, this is the equation of the control action. Okay, so in the first segment, so this is OPQ, and let me just name the same. What was this? OPQR. Okay, Q and this is R. Okay, so if you take the segment OP. Okay, in this segment, how do we evaluate the control action? So I will call the control action to be P1, the control output to be P1. So it is 2 into EP plus 2 into 2 dEp by dt plus 40. So this 40, which is P0, will always be added at each and every step. Okay. Now we do not have any integral control action here, we don't need to store any kind of control for the next step. Okay, so you are actually calculating some kind of instantaneous outputs. Okay, so now P1 would be written as 2t plus 4 plus 40, and it comes to 2t plus 44. Okay, so this is for t is equal to 0 to t is equal to 0 to 2. Okay, so at t is equal to 2, this is little interesting. You will find at t is equal to 2, you will see that P1 will be equal to 48. Okay, make a note of this. Okay, make a note of this. P1 is equal to 48 at t is equal to 2 seconds. Okay. Now let's get back to the next segment. Alright, next segment is segment PQ. Segment PQ. So now the control action P2 is 2 into, depending on the error equation, 2.5t plus 7 plus 4 into, you have to take the derivative of the error, so you get minus 2.5 plus d by dt of 7 is 0, this is 0 plus 40. Okay, so what would happen now is you have P2, which is minus 5t plus 44, and t is varying from 2 to 4. Alright, now at t is equal to 2, what do you think with this equation will do, right? So you will find that P2 is equal to 34 at t is equal to 4. P2 will be equal to, P2 is equivalent to 24. Okay. So however, in the previous slide, you saw that at the end of time t is equal to 2, you found P1 to be 48. That means in the next step, you are seeing at the end of time, in the beginning of time t is equal to 2, you are seeing that the control output has jumped to 34. Okay, we need to plot and see how this works. And at the end of this time, you are getting the control output to be 24. That means there is a significant jump between the steps. Okay. Now let's take the segment QR. Let's take the segment QR where you change the time from 4 to 6 seconds. Okay. Now what is controller output P3? The controller output P3 is equal to 2 into 1.5t minus 9 plus 2 into 2 into 1.5 plus 40. Okay, so P3 would come to be, let me just write this as, comes to 3t plus 28, and t varying from 4 to 6. Okay, so at t is equal to 4, what will happen? At t is equal to 6, what is going to happen is what we need to see. So the control action would give you this P3 would be equal to 40, and this would be around 56. Okay. At t is equal to 4, you got 24 previously, and in this step you are suddenly getting 40. So you will see a sudden rise in the derivative. Of course, as we know that whenever there is an error curve like this, whenever this error is increasing, okay, and when there is a change in slope, you would see a significant change in the integration. Okay, sorry, the derivative, because you are changing the slope. You are getting d by dt. Okay, so let's try to plot the whole thing now. So let me just put this whole thing in the same plot. Okay, let me just take this as time t. This is the control output p. Okay, so initially you started with some 44, and let me just this is 2, this is 4, and this is 6. Okay, let me just draw some lines like this for convenience. Okay, now you started at 44. Okay, the first time you started at 44 and reached 48 in the time slot what you see here in the first segment, right? In the first segment at t is equal to 0, you have 44, and then you jump to 48. So 44 to 48 is what we need to draw for the first segment. Okay, so this is 48. So you have gone up to this point in the first segment. Okay, then in the second segment, you see that you came to 34 at the same time interval, and you have jumped to 24. So 34 to 24 is what we need to do. Okay, 34 to 24. Okay, so you have something called 34 here, That means in the same segment you came back here, and this is 24. That means there is a jump from here to here. Okay, just draw this properly here, and then you made a jump here, and then from here to here you are trying to draw this line. Okay. Now similarly in the third segment you see that you had a jump from the previous segment, you had 24, but in the third segment you at the same value of time you had 40, and you are jumping to 56. Okay, so you would have this value somewhere is to be 40. That means in the third segment you will reach 40 first, and from there you would go to 56. Okay, 56 may be somewhere here. Okay, so that means from here you are going to 56. Okay, so what you can see here clearly is that you are jumping here, right? This is the transition point which you are having with respect to this controller. Okay, this is to do the derivative action, especially when there is a change in slope. Okay, so these are the transition zones which you will need to plot in the derivative controllers properly. Okay, so this is fundamentally due to the fact that the derivative controller adds Kp into Kd into the P by dt term. Okay, this is the term which gets added instantaneously at every transition. All right, so this is the way you need to plot the derivative control action. So I hope this clarifies how to plot the curves for PI and PD controllers. PD is little tricky. Okay, PI is little easier because the integral control takes care of the actual plot. Okay, so this ends this lecture. Thank you.